More than 700 kilometers of concrete, barbed wire, and electronic fencing have turned Israel's border into a structure worth more than $1.7 billion. But this is not just a wall. It is the place where security, territory, and conflict collide directly. It does not run through a simple empty land, but cuts through complex terrain, sensitive areas, and hotspots that have been pulled by tension for decades. Therefore, each section of the wall is not only built to separate, but also reflects how Israel tries to control a border that is constantly changing. And it is here that the story becomes much more complicated. Something built to create a sense of safety also deepens disputes over land, sovereignty, and the future of the entire region. In this video, join Mandarin Tech as we explore how Israel built one of the most complex border wall systems in the world. Israel lies on a narrow strip of land in the eastern Mediterranean, bordering many areas with important strategic positions in the region. With complex terrain and long border lines, controlling security cannot rely only on traditional patrols. The biggest problem Israel faces is the risk of illegal infiltration, weapons smuggling, and attacks through border sections that are difficult to monitor. In many places, residential areas, roads, and controlled zones are very close to one another, meaning that even a small gap can create a major risk. Since 2002, Israel has begun building a system of security fences and walls to create a clearer layer of defense on the ground. This structure is not only made of concrete or barbed wire, but also combines patrol roads, cameras, sensors, and checkpoints. Its goal is to detect unusual signs early, slow down the risk of infiltration, and help security forces respond more quickly. Unlike building a tower or a bridge, a border wall is a complex structure with many hidden risks. Because of this, clearing the construction site is almost like opening a long cut across the terrain. The first step is surveying and route alignment. Engineering teams use GPS, total stations, and topographic maps to accurately determine the path of the structure. They then place survey stakes, stretch guidelines, and mark the entire construction corridor. At the same time, geological drilling machines begin taking soil samples at multiple locations, usually drilling to depths of about 10 to 30 meters depending on the terrain and type of structure, in order to determine the soil type, load-bearing capacity, and risk of settlement. In rough terrain, land leveling becomes a major challenge. High-powered bulldozers of up to 400 horsepower continuously cut down raised ground and fill low-lying areas to create a relatively stable surface. Once the ground reaches the designed elevation, vibratory rollers begin their work. Each layer of soil is compacted repeatedly to increase density and load-bearing capacity. In sections prepared for concrete walls, excavators dig foundation trenches about 2 meters deep according to the design dimensions. Crushed stone is spread along the bottom of the trench to create a drainage layer, after which steel reinforcement cages are installed before concrete is poured for the foundation. This foundation will carry the entire weight of the walls several meters high above it, while also resisting wind pressure, vibration, and changes in the ground over time. The entire foundation preparation process can take many months before the first meter of wall is finally erected. While most of the borderline uses a security fence system, in densely populated urban areas, or in places where the distance between the two sides is only a few dozen meters, Israel chose to build reinforced concrete walls. These structures not only serve as physical barriers, but also limit direct visibility between the two sides in areas with high population density. The concrete wall sections are often up to 9 meters high, equivalent to a 3-story building. Instead of being fully cast on site, many wall panels are produced in precast concrete factories, with concrete strength reaching 50 megapascals. There, steel molds are assembled to standard dimensions before the load-bearing reinforcement is placed inside. When everything is ready, cranes with a lifting capacity of up to 100 tons begin lifting each concrete panel off the transport truck. The crane operator works together with the signal team on the ground to slowly rotate each massive concrete block into the correct position. This work requires extremely high precision because the gaps between the panels are measured in only a few centimeters. From a distance, the concrete walls form a continuous structural strip, rising far above the surrounding buildings. However, behind every meter of wall is the coordination of many stages, from material production to the completion of technical infrastructure. It is this precise construction process that helps the structure maintain stability under harsh weather conditions and operate continuously for many years. Not the entire borderline is built with massive concrete blocks. Along most of its length, especially in open terrain areas, Israel uses a multi-layered steel fence system, which is flexible in construction while also allowing patrol forces to see through it and monitor the situation on both sides of the borderline. The installation process begins with locating each post position. Along the corridor that has already been cleared and leveled, engineering teams use GPS, total stations, and design drawings to mark the exact spacing between the posts. Depending on terrain conditions, this spacing ranges from 2.5 to 4 meters, close enough to maintain stability along the entire line while still allowing fast construction across terrain that stretches for hundreds of kilometers. Once the main post system is stable, workers begin installing horizontal braces, connecting frames, and steel mesh panels. These mesh panels are usually stretched section by section and fixed with bolts, steel clamps, or specialized binding wires. The tension must be carefully controlled. If it is too loose, the fence can easily vibrate and deform. If it is too tight, the connection points may become overloaded over time. After the steel mesh has been firmly stretched, workers reinforce the fence base with a low strip of cement or concrete running along the line. Temporary formwork boards are set close to the lower edge to hold the pour in shape. The mixture is then placed at the base, covering the contact between the ground and the mesh edge. Workers use trowels and hand tools to level the surface and compact the material around the structure. Once hardened, this base strip secures the lower mesh, limits erosion, and makes digging underneath harder. In many sections, the fence is not only a physical barrier. Vibration sensor cables are attached along the body of the fence to detect unusual impacts such as cutting, climbing, or strong collisions. When a change in signal is detected, the data is transmitted to the control center. Thanks to this, the steel fence line becomes part of an active surveillance system, where the metal structure, measuring devices, and patrol forces work together to detect and respond quickly to the risk of infiltration. After the main structure is completed, the project continues to be reinforced with barbed wire and razor wire. This is an additional protective layer designed to extend the time needed to get past the fence, while also increasing the ability to detect infiltration attempts. The wire coils are made from high-strength steel and coated with an anti-corrosion layer so they can operate for many years under hot sunlight, sandy winds, and constantly changing humidity. Each coil has a large diameter, significant weight, and is transported to the construction site by specialized trucks. During installation, workers use forklifts or small cranes to lift each coil onto the top of the fence. The coils are then stretched along the length of the line and fixed to pre-installed steel supports. This work requires careful coordination because the wire has very strong tension. Just one wrong movement can create danger for the workers. In high-security areas, multiple layers of wire are arranged in parallel or stacked in a pyramid shape to make access more difficult. Some sections are also combined with night lighting, vibration sensors, and infrared cameras to create several consecutive layers of protection. The installation is not only meant to block access, but also to guide movement. Controlled openings direct all movement through border crossings or checkpoints, where security forces can carry out inspection procedures according to regulations. A modern borderline does not consist only of walls and fences. Along its entire length, observation towers, monitoring centers, and checkpoints are placed at intervals, forming a management network that operates continuously. Observation towers are usually built in locations with a wide field of view. From there, Personnel can directly monitor the surrounding area or track images from multiple camera systems connected to the control center. Cameras are installed at suitable intervals depending on the terrain. In addition to standard optical cameras, the system also includes infrared cameras, thermal cameras, and night vision devices, helping maintain surveillance capability in low light, fog, or unfavorable weather conditions. Underground, different types of sensors are placed to detect vibration, movement, or unusual activity. Data from these devices is transmitted back to the control center through fiber optic cables and dedicated communication networks. The control center is where data from the entire borderline is collected. Software analyzes signals from thousands of sensors, cameras, and other devices to detect events that require attention. When an alert appears, personnel can quickly verify it through live images before dispatching patrol forces. At border crossings, control is carried out through multiple steps. People and vehicles passing through these areas go through document checks, security checks, and cargo inspections according to current regulations. Thanks to the combination of physical infrastructure and technology systems, the entire borderline operates as a continuous surveillance network rather than just a passive barrier. After construction is completed, the work does not stop there. A borderline hundreds of kilometers long requires continuous operation and maintenance for many years. Maintenance teams regularly inspect the condition of the fences, concrete panels, foundations, and wire systems. Areas affected by corrosion, cracks, or damage are repaired or replaced to maintain operational capability. Electronic equipment also needs to be calibrated periodically. Cameras must be cleaned and replaced when image quality declines, while sensors are checked to minimize false alerts. The climate in this region creates many challenges. Prolonged heat can affect electronic devices, while strong winds and sandy dust accelerate the wear of mechanical components. Beyond natural conditions, the system must also adapt to technological changes. New surveillance devices offer higher resolution, faster data processing, and artificial intelligence integration to help detect unusual situations. Because of this, upgrades are carried out in stages instead of replacing the entire structure at once. This helps reduce costs while maintaining continuous operation. In the far west of China, between two towering mountain ranges, lies the vast Taklamakan Desert, an endless ocean of sand at the heart of Xinjiang. Before the highway existed, crossing this land meant walking for weeks, even months, through one of the harshest environments on Earth, where surface temperatures can soar above 70 degrees Celsius, and sandstorms can swallow entire convoys in just minutes. Yet beneath that sea of sand lies a hidden treasure, enormous reserves of oil, natural gas, coal, and rare earth minerals. Strategic resources that have helped China strengthen its global position. To extract, transport, and connect Xinjiang with the rest of the country, Beijing had to attempt the unthinkable: build a highway straight across the Taklamakan Desert, a place once deemed an impossible blind spot for engineering. The Luntai-Minfeng Expressway, stretching more than 522 kilometers, began construction in 2017 and was completed in 2021, becoming China's first and longest desert-crossing highway. And the construction of the highway started from scratch, in the middle of a sandy desert. How do you build a highway across a desert that never stops moving? They began with high-resolution satellite imagery, ground-penetrating radar, and thousands of wind measurements to map the shifting dunes and find pockets of stable ground. Survey teams lived deep in the Taklamakan for months, drilling hundreds of boreholes, some more than 30 meters deep, to study the layers hidden beneath the sand. Every route marker was staked by hand and logged with centimeter-level precision. The highway had to avoid the wind corridors, where sandstorms could bury an entire road overnight, yet stay close enough to reach the oil and gas fields spread across the Tarim Basin. It was the first step in turning what had long been a blank white void on China's map into a black ribbon of pavement cutting across the heart of the desert. Before any concrete was poured or asphalt rolled, The project began with an unexpectedly low-tech mission, anchoring the sand. Hundreds of local farmers from small oasis villages along the desert's edge were recruited, earning between $80 and $100 a month. A humble income, but one that kept their families afloat. Their job sounded simple, yet it would determine whether the entire highway could exist at all. Bundles of straw, twigs, and thin bamboo were tied into long sheaves and driven deep into the dunes, forming a vast checkerboard pattern. Each square measured 1 meter by 1 meter, laid diagonally at 45 degrees to deflect the wind and trap sand inside the grid. Under a sun that pushed the air above 60 degrees Celsius, hot enough to bend metal, teams of a dozen men and women planted grid after grid across the desert floor. They wrapped their faces in cloth, soaked their hats with water, and worked in silence against the relentless wind. Within months, the transformation was visible. More than 1,000 hectares of straw grids pinned the dunes in place. Wind velocity near the ground dropped by 40%. The sand began to crust and harden, and for the first time, heavy trucks could cross without sinking. The checkerboards didn't just stabilize the site, they created new zones of life, protecting nearby villages and giving native desert plants a foothold again. From this quiet, back-breaking labor rose the first layer of an engineering triumph. On that newly anchored sand, the construction of the Taklamakan Desert Highway could finally begin. After the sand surface had stabilized, the next challenge was to reshape the terrain. Hundreds of bulldozers were deployed to flatten the dunes, cutting down the high ridges and redistributing the sand into lower areas. The goal was to create a smooth, balanced surface strong enough to support construction machinery without the risk of collapse. Each section was carefully scraped and leveled under strict supervision, with surveyors checking elevation and slope to ensure uniformity across miles of open desert. Conveyor systems pushed the excess sand away from the work zone, while compactors gently pressed the top layer to form a firm and workable foundation. After the bulldozers had leveled the dunes, the sand still needed to be stabilized. Engineers discovered that injecting water into the loose surface helped bind the grains together, creating a denser and more cohesive layer. Using long sprinkler arms and underground pipes, they sprayed controlled amounts of groundwater across the site, allowing moisture to penetrate several inches deep. Once the sand reached the right level of dampness, heavy rollers moved in, compacting the surface to remove air pockets and lock the particles in place. The constant rumble of steel drums echoed across the desert as each pass of the roller turned soft, shifting sand into a firm, uniform base. By the time the surface dried under the desert sun, it had hardened enough to carry the weight of cranes, mixers, and supply trucks. A solid foundation built from nothing but sand and water. After the surface had been compacted, workers began spreading a base layer of soil over the stabilized sand. Dump trucks poured out loads of reddish earth, which bulldozers then pushed and leveled across the area. This layer added weight to the sand below, strengthening the surface and keeping it from shifting under heat or vibration. Each section was evenly spread and compacted, forming a dense, stable base strong enough to support the first stages of construction in the desert. Beneath the desert highway, the foundation had to be rebuilt from the inside out. The Taklamakan sand was fine and dry, unable to bear the weight of even a single truck. Engineers drove sand compaction piles and mixed cement directly into the soil, creating dense vertical columns that acted like roots beneath the road. In looser areas, geogrid mats, strong synthetic nets, were laid down to spread the load evenly. Once reinforced, convoys of dump trucks arrived, pouring crushed stone and grated gravel across the route. Bulldozers spread the mix into layers 20 to 30 centimeters thick, followed by vibratory rollers pressing it into a solid platform. By the end of this stage, the pale gray subgrade stretched like a giant runway through the dunes, ready for its black asphalt skin. At the edge of the desert, portable asphalt plants roared to life, heating stone, sand, and polymer-modified bitumen to nearly 170 degrees Celsius. From these stations, insulated tankers delivered the hot mix non-stop to the paving machines waiting on site. Each paver spread the glowing asphalt in layers about 6 centimeters thick, while steel rollers followed close behind, compacting it before it could cool. This process was repeated in a tight choreography, paver, roller, finisher, moving forward like a synchronized machine. The first passes used heavy steel drums for compression. The final ones switched to rubber tire rollers, which kneaded the surface to seal tiny air gaps and create a smoother texture. Thermal sensors on each paver tracked the surface temperature in real time. If the asphalt dropped below 140 degrees Celsius, rolling stopped immediately. Otherwise, cracks could form once it cooled. Supervisors checked flatness with laser beams, allowing no more than 3 millimeters of deviation per meter. As the desert wind cooled the surface, the asphalt hardened into a flawless black sheet, tough enough to withstand temperature swings from minus 25 to plus 70 degrees Celsius. To finish, workers sprayed a protective seal coat, giving the surface its signature deep shine and locking out moisture. By dusk, the newly paved highway gleamed under the sinking sun, a dark, mirror-like ribbon stretching across the golden sea of sand. What had once been an empty wasteland now reflected the light of progress, born from heat, steel, and human endurance. So after 4 grueling years of construction, the 4-lane highway cutting across China's largest desert finally stood complete, a powerful testament to human determination and technological mastery in the heart of the Sea of Death. This project not only connected the far ends of Xinjiang, but also showcased an engineering achievement so remarkable that even American engineers couldn't help but be impressed. But the story didn't end there. What came next left even seasoned American engineers astonished. A project on an even grander scale. Stretching boldly across the same unforgiving sands of the Taklamakan, China began constructing an elevated railway, a steel ribbon suspended above the desert, defying heat, wind, and time itself. The Hotan-Rokiang Railway, stretching 825 kilometers, is part of the larger Taklamakan Desert Loop Railway, which spans more than 2,712 kilometers. Construction began along the southern rim of the Taklamakan Desert and was completed in June 2022, making it the longest desert crossing railway in the world. More than 65% of the line, over 500 kilometers, was built on elevated concrete viaducts supported by more than 11,000 pillars. This design allows desert winds to pass freely underneath, preventing sand from bearing the tracks. The first steps to build a railway track are to fix the soil and sand foundation, which is exactly the same as building a highway, so I won't repeat it again. Once the ground base was fully stabilized, workers began erecting the bridge pillars. To build them, they had to drill through dozens of feet of loose sand until reaching the solid gravel or compact soil beneath. Reinforced concrete pile drivers operated day and night using steel casing pipes and bentonite slurry to keep the boreholes from collapsing. Concrete was poured from the bottom up through tremie pipes to prevent air pockets, while the steel cages were positioned with millimeter precision. Even the slightest misalignment could cause the pile to tilt or lose stability. Because daytime and nighttime temperatures differed by more than 130 degrees Fahrenheit, construction crews worked mostly at night, when the wind was calm and the sandstorms eased. Thanks to these steel and concrete piles, the railway's foundation seemed to grow roots deep into the desert. On top of those foundations, 11,000 bridge piers began to rise, row after row, forming a vast concrete forest stretching across the desert. Each pier stood between 16 and 50 feet tall. The shafts were cast using slip-form molds, reinforced with galvanized steel and salt-resistant additives to withstand the desert's corrosive climate. The short, uniform spans between piers were designed to minimize the effects of wind and extreme temperature changes. As the sun set behind the Kunlun Mountains, the endless lines of pillars stretched toward the horizon, a skeleton of steel and concrete, unshaken by the desert winds. On top of those pier caps, thousands of pre-stressed concrete box girders were lifted into place using heavy crawler cranes or self-launching gantries. Each girder was over 100 feet long and weighed several hundred tons. They were transported on specialized flatbed rail cars and hoisted one by one onto the piers. Engineers then aligned the girders with laser precision, keeping tolerances within just a few millimeters. Once the spans were secured, crews poured the bridge deck slabs or installed precast concrete panels, forming a smooth surface for the tracks. Every span was spaced to allow wind to sweep freely beneath, carrying drifting sand away so it could never bury the line. More than 65% of the Hotan-Rokyang Railway, about 310 miles, runs on these elevated viaducts. From above, the railway appears like a silver ribbon cutting across an ocean of gold, a living monument to human ingenuity against one of Earth's harshest landscapes. Next, these concrete blocks being installed are called sleepers, or railroad ties. They're placed evenly along the track bed to hold the steel rails in position and distribute the weight of passing trains. Workers align each sleeper precisely, then use a lifting frame to lower the rails onto them. Once fixed and fastened, they keep the track straight and stable, preventing it from bending or shifting under heavy loads. A crucial step before the trains can safely run through the desert. After the sleepers were secured, crews began laying the steel rails on top. Each rail, stretching more than 260 feet long, was lifted into place by specialized cranes and carefully aligned along the center line. Workers adjusted every joint and gap to allow smooth expansion under heat, then tightened the fastening clips that locked the rails onto the concrete base. It took 11 months of continuous work to complete the hundreds of miles of track stretching across the desert. When the final bridge span was completed, the entire line entered the testing phase. Engineering trains ran up and down the route to measure settlement, vibration, rail temperature, and wind-induced sway. The bridges were load-tested with trains weighing thousands of tons. Results showed elevation deviations of only a few millimeters, even after hundreds of test runs. Thanks to the elevated design and natural airflow beneath the viaducts, no sand accumulated on the tracks. All operational data flowed to the control center through IoT sensors and solar-powered cameras that monitored every section in real time. After 6 months of rigorous testing, the Hotan-Rokyang Railway officially opened in June 2022, completing the 1,685-mile loop that circles the Taklamakan Desert. So you have learned the whole process of building a road through China's largest desert. If you are impressed, follow Mandarin Tech so you don't miss any interesting videos.